So we're going to mostly be doing rational because that's when vertical asymptotes come up. So the first thing on this example that we should do is factor the denominator so we can kind of see if we have asymptotes, which obviously we're going to, or if we have wholes, and maybe we have a little bit of each. So on this first example, you would factor your denominator into what? X plus 4, x minus 2. So this particular function, is it going to have a whole? Yes, there's a whole at 2. 2 what? What would the coordinates be for your whole? 2 what? 1/6. Because this function is essentially simplified to 1 over x plus 4. So the graph of this one and the graph of this one are going to look virtually identical with the exception of the whole. Because this one on its own wouldn't have a whole. It would actually have a point at 2/6. But knowing that we're really truly trying to graph this one, we're going to have a whole at 2/1/6. Did I say 2/6? I meant 1/6. Does everyone see that? Okay, so your whole is at 2, and then when you plug in 2, you get 1 over 2 plus 4, which is 1/6. Where's our asymptote? -4. So we have an asymptote at -4. So when you're dealing with an asymptote, a vertical asymptote, the limit does not exist, right? We talked to just what the word limit means. What is the limitation as you approach an asymptote? We know from the work we've done with vertical asymptotes that graphs always approach infinity or negative infinity. So kind of just with that logical thought of, well, then what's the limit? There is no limitation if you're going towards infinity. However, we can, even though the overall answer is does not exist, in this we give a more specific version of how it doesn't exist, meaning if it goes towards positive infinity, we say that. Even though we know that positive infinity is a more specific version of does not exist, you're going to give the most specific answer. So you're not going to write does not exist if you're approaching -4 from the right. So if you want to do a quick sketch to wrap your head around what's going on, we have an asymptote at -4. And we want to see what happens as we approach that from the right. So, I mean, you could plug in something like -3.99999. You're not going to get an exact value when you do that, right? Because we don't have a calculator. But if you think about plugging in -3.999 plus 4, that's going to be 1 over a positive or a negative number? Positive, and it's a really tiny number, right? -3.99999 plus 4 is going to be like positive 0.00001 or something. So just loosely speaking, without this needing to be exact, because we're just sort of brainstorming here, what is 1 over a positive tiny number? A really big positive number. And again, we don't care about the number. We already know the answer is going to be infinity or negative infinity. We've just realized that it's positive infinity. Yes? By doing that? So this is positive infinity. Now, if you're approaching -4 from the left and just brainstorming, you would maybe plug in like -4.0001. Right? That would be slightly to the left of your asymptote. And if you do that, your denominator is going to be very slightly negative, right? Because the magnitude of your negative number is outweighing your 4. So it's going to leave you -0.0001. And 1 over a tiny, tiny negative number is going to be negative infinity, right? How else could we know that that was probably what was going to happen based on what we know about vertical asymptotes? Jalen? Not always, but in this case, yes. What is that? Sometimes they do both go towards positive infinity. What cause? Exactly. So it's the degree of our asymptote. We've talked about that before. If the degree of your asymptote is even, the behavior on either side of the asymptote kind of works and jives together. They both go in the same direction. But most often our asymptotes only have a single degree, so most often we get used to when you're coming from one side going towards positive infinity, when you're coming from the other side going towards negative infinity. Now, in this scenario, when they go and they ask for the overall limit, we've done from the right, we've done from the left, we have more specific versions of does not exist in those cases. In the overall limit, though, we can't give a more specific version of does not exist because they don't even, the more specific versions we have don't even go together. So because they are different, we will still, on this one, end up with does not exist. And then in part D, I asked about the whole. So what happens as we approach 2? Does the limit exist when you're approaching a whole? Yes. Okay, so this graph is going to look something like this with a hole at 2 and 1/6. So there's an open circle there before it carries on. So as you approach, and I didn't break this one down, approaching from the left, approaching from the right, but if you look at it, approaching from the left, I'm right here, approaching from the right, I'm right here, and they're kind of pointing at each other. Therefore, your limit does exist, and the answer is what? 1/6. Good. Okay? So, when you approach vertical asymptotes, we're trying to figure out which infinity we're dealing with. And you sort of, unfortunately, there's no other instruction other than kind of brainstorm with it, given that you know some of the behaviors surrounding asymptotes, like in this case, they're opposite of each other, but also you're exploring by plugging in the concept of certain numbers without actually having a calculator at your fingertips to be able to calculate it. Because even still, calculating and realizing that this was 1,000 isn't really going to be your answer anyway. It's all for the sake of deciding positive or negative infinity. Okay? Any questions? All right, so then on our next function, we're going to do the same thing. Factor the denominator. And obviously my intention in this case was to talk more about that degree piece that Jalen just brought up. So we're approaching an asymptote at 3. You don't have to sketch it, but I like to. As we approach 3 from the right, so what kind of number could we plug in? Nathan McMillan. Right. And honestly, I went a little overboard. You really, just because we already know it's one of the infinities, you could just plug in 3.01. You could plug in 3.1 and it should be pretty accurate. So if we do that, and I would obviously recommend plugging into here, 2 over 3.01 minus 3 squared is obviously going to give us a positive tiny number. Square that tiny number, it's going to be even tinier. And it's going to be positive, right? 2 over a positive tiny number. 2 over positive tiny. I'm just writing that so that we can remember what we were thinking. And that's going to be positive infinity. And then if we're approaching 3 from the left, 2.9 should be good enough to check. So if you brainstorm with 2.9, this should give you some physical evidence as to why that asymptote being squared causes them to go in the same direction, right? Because we're going to get a negative number, but when you square it, it's still going to be positive. And so obviously you're still left with positive, a tiny number on the denominator. And so you still get positive infinity. You don't need to write the positive sign. I'm just doing it to accentuate the fact that it was a discussion, that that's the big if, positive or negative. And then for part C, because they match, again, the limit is still does not exist, but at least in this case, the more specific version of does not exist agrees with each other, and we can say that that's also positive infinity. So what we have happening is, from the right and from the left, they're both going towards positive infinity. And then part D is kind of out in left field. What would you do without me talking you through it? What would you do to find a limit as x approaches 1? All right, just plug it in. There's no special thing happening at 1. It's not an asymptote. It's not a whole. So direct evaluation should be no problem. So we would just say 2 over 1 squared minus 6 times 1 plus 9. 1 minus 6 is negative 5. Negative 5 plus 9 is 4, so this is 1/2. Good? Any questions? Okay. Coming away from rationals. The tangent of x has lots of asymptotes, doesn't it? Remind us, where are the asymptotes for a trig tangent graph? Where is tangent undefined? Go ahead, Jalen. Pi over 2, 3 pi over 2, any odd pi over 2, right? Negative pi over 2. Yes? Okay. So in this case, the graph is going to be more efficient, because why plug in a number slightly to the right of pi over 2 if you know what the graph looks like, right? There's no hard and fast rule. When do I plug in a number to check it? When do I use the graph to check it? You kind of want to do what's more efficient, and that's going to change based on the situation, okay? For the rationals, we really can't even come up with the graph until we think about plugging in a number. Here, on the other hand, because we should know the tangent of x graph so well, we don't really need to worry about plugging in numbers. We should know that it does this, right? And then don't worry about plugging in numbers, because we do know the graph so easily. When you approach pi over 2 from the right, what's our answer? Stephanie. Nope. We're approaching pi over 2 from the right. Negative infinity. Here we're approaching pi over 2 from the left. So that's positive infinity. And therefore, Kendall, what's our answer for the overall limit as we approach pi over 2? Good. And then how about our limit as we approach pi over 4? What do you think we should do, Winter? Just plug it in, because pi over 4 is not a whole, it's not an asymptote, so it should be able to be directly evaluated, and the tangent of pi over 4 is 1. You forgot, right? It's been so long. Oh boy, we got to go into that again. Tangent of pi over 4 is 1. You think? Do you agree with that, Adam? Okay. Any questions on that? Log graphs and exponential graphs. Let's do a quick review, because it's been a while since we've done those. Exponential graphs have what kind of asymptotes? Horizontal. Okay? So that's y equals some base to the x power. Log graphs, which is what this example is, have a vertical asymptote and do this. So y equals log base b of x. So this is why we bring up a log graph, is because today the focus is on vertical asymptotes. So let's think about where this vertical asymptote is. And there's a couple ways we can think about it. Number one would be regarding transformations. How has the parent graph been shifted? 3 units to the right, which means my vertical asymptote is now shifted 3 units to the right as well. Yes? So that would be the graphical, visual way of thinking about where that asymptote is. The other would be thinking about the domain of log graphs and the fact that you can only take the logs of what kind of numbers? Positive. So algebraically, you know that x minus 3 has to be greater than 0, has to be positive, and then x has to be greater than 3. And that's the asymptote. I mean, those two thought processes, whether you think about it graphically or you think about it algebraically, they do jive with each other, right? They kind of are one and the same, although, you know, you might think of it totally differently in one way versus the other. But regardless of which way your brain thinks, we all now know we have an asymptote at 3. Yes? The vertical stretch compression doesn't really do much for us. So, again, here's a case where the sketch of the graph is just more efficient. Because without a calculator, plugging in 3.001 isn't going to do anybody any good. So we would just know that this kind of got stretched vertically a little bit, but that's not going to change the behavior of the graph as we approach the asymptote. So as we approach 3 from the right, what's our limit, Michelle? Negative infinity. How about as we approach 3 from the left? This may or may not have already come up in this class. It came up in some of the classes based on a homework question that people had. What does your gut tell you, Kyle? Correct. Have we talked about that? No. It came up in some of the classes. If the graph doesn't exist to the left of the asymptote, or to the left of any number, if the graph doesn't exist, then there's no way the limit can exist if you're coming from that side, because there is no way to come from that side. So you would just say does not exist here, because there's no way of approaching this 3 value from the left. And then obviously the overall limit can't exist. How about the limit as we approach 5? Thoughts there? Just plug it in. So we'd have to make sure we can do this without a calculator, which I chose a number that we can do without a calculator. That simplifies to log base 2 of 2. What is log base 2 of 2? 1. So 2 times 1 is just 2. So direct evaluation, again, you start to get a sense for, is direct evaluation going to work here or not? And it all depends on if something finicky is happening on the graph at that value. Here, something finicky is happening. We have an asymptote. Here, there's no twist and turn. This is very straightforward. The graph is continuous at 5. We don't have a hole, we don't have a jump, we don't have an asymptote, so you can just directly evaluate. How about at 1? Right, does not exist. If the function doesn't exist at 1, there's no way the limit can even exist there. Okay, so knowing your graphs, knowing the basics of the features surrounding different types of functions is hugely important, because you're not going to be able to just plug in a number without a calculator all the time. Okay? So understanding how graphs behave surrounding asymptotes, surrounding holes, understand where they exist and don't exist in general is hugely important. I am going to give you a worksheet and you don't have to write this down, but as long as we have another minute to talk about it, we're also going to talk about graphs that not just they might not have an asymptote, but like, what is this the parent graph of? Do you know? Square root of x. Square root of x. So this is y radical x. Something like this. Let's say I shift it, I don't know, 2 units to the right. So something like that. And I didn't include this on this day because there's no vertical asymptote here, but there's still a conversation that we should have about what is the limit as we approach certain values. So anytime we approach a value over here, like 3, 4, 5, 6, 7, easy. It's just directly evaluating, right? If we approach 2, we need to have a conversation, because from the left and from the right, we have a conversation. What is the limit as you approach 2 from the right? Here's 2. As I'm approaching 2 from the right, what's my limit? 0. What is my limit as I approach 2 from the left? Does not exist because the graph doesn't exist. And then, so my overall limit does not exist either. And then if they ever ask me for the limit as x approaches -5, not even worth talking about if the function doesn't exist. Do you follow? Any questions? Okay. I'm going to give you your worksheet.